This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into the paper VilBias, a study of bias detection through linguistic and visual cues, which tackles the crucial issue of bias detection in multimodal news content. The authors propose a novel framework leveraging LLMs and VLMs. What are the key limitations of existing approaches to bias detection that VilBias aims to overcome?
Existing text-based bias detection methods often fall short because they neglect the crucial interplay between textual and visual elements in news content. Subtle biases can be embedded within images, their cropping, or the juxtaposition of text and visuals, which traditional methods miss. Furthermore, creating high-quality, labeled datasets for training and evaluating these models is expensive and time-consuming, hindering progress in the field. VilBias addresses these limitations by proposing a multimodal approach and a hybrid annotation strategy.
The hybrid annotation strategy is a core component of VilBias. Can you elaborate on its design and the rationale behind combining AI-based labeling with human review?
The hybrid approach uses LLMs and VLMs to generate initial annotations, significantly reducing the cost and time associated with purely human annotation. However, the subjective nature of bias necessitates human oversight. Human reviewers validate the AI-generated labels, ensuring accuracy and addressing nuances that LLMs might miss. This combination aims for scalability without sacrificing quality. The two-step voting mechanism, first among multiple queries per model and then across models, further enhances reliability.
The paper mentions the use of both small language models, SLMs, and large language models, LLMs. What are the key differences in their performance in this context, and why is this significant?
While SLMs offer computational efficiency, LLMs demonstrate superior accuracy, particularly in identifying subtle framing and inconsistencies between text and visuals. This is because LLMs, trained on massive datasets, possess a richer understanding of language nuances and contextual information. The choice between SLMs and LLMs involves a trade-off between computational cost and accuracy, with the optimal choice depending on the specific application and resource constraints.
The paper highlights a 3–5% improvement in bias detection accuracy by incorporating visual cues. Can you discuss the specific ways in which visual information contributes to more accurate bias detection?
Visual cues provide a crucial layer of context that textual analysis alone often misses. For example, the cropping of an image can subtly emphasize or de-emphasize certain aspects of a scene, thereby influencing the narrative. Similarly, the choice of imagery emotive or neutral can significantly impact the reader's perception. Analyzing the interplay between text and visuals allows for a more holistic understanding of potential bias.
The paper evaluates several state-of-the-art LLMs and VLMs. What were some of the key findings regarding their performance, and what factors influenced their success or failure?
The results showed that instruction fine-tuning consistently outperformed zero-shot and few-shot approaches across both LLMs and VLMs. This highlights the importance of tailored training for specific tasks. Larger models generally performed better, but smaller, more efficient models like RO-BERT also showed strong performance, particularly in text-only classification. The choice of model depends on the balance between accuracy and computational resources.
The paper also includes ablation studies. What insights did these studies provide into the impact of data size and fine-tuning techniques on model performance?
The ablation studies confirmed that LLMs are more robust to reductions in training data size than SLMs. They also demonstrated the effectiveness of parameter-efficient fine-tuning methods like LORA, which achieve near parity with full fine-tuning while significantly reducing computational costs. This is crucial for deploying these models in resource-constrained environments.
The qualitative analysis provides valuable insights into the model's reasoning processes. What were some of the key observations regarding the model's ability to identify and correctly classify bias?
The qualitative analysis revealed that while the models often correctly identified overt biases, they sometimes struggled with more subtle biases or relied on stereotypes in their reasoning. For instance, some models exhibited a tendency to over-rely on textual cues, neglecting visual context, or vice versa. This highlights the ongoing need for improved context-aware multimodal reasoning in these models.
The paper concludes by discussing the practical and social impact of VilBias. Can you summarize the potential applications and broader implications of this research?
VilBias offers a scalable framework for detecting bias in multimodal news content, with applications in content moderation, journalism, and public policy. By revealing hidden biases, it can promote more equitable media practices, increase transparency, and foster greater trust in digital information. The hybrid human-machine approach ensures both scalability and accuracy, addressing a critical need in the field.
What are some of the limitations of the current VilBias framework, and what are potential avenues for future research?
The current dataset, while diverse, may not fully capture global cultural and linguistic nuances. The framework also primarily focuses on biases readily detectable through textual or visual cues, potentially missing more subtle, systemic biases. Future research should focus on expanding the dataset's scope, incorporating more granular bias categories, and developing more sophisticated methods for capturing context-dependent biases. Addressing the computational cost associated with large models is also crucial for broader adoption.
The paper mentions the use of several different LLMs and VLMs. Could you elaborate on the selection criteria for these models and the rationale behind choosing a specific set for the experiments?
The selection of LLMs and VLMs aimed for a balance between established models with proven performance and newer, more advanced architectures. The inclusion of both small and large models allowed for a comparison of computational efficiency versus accuracy. The choice of specific models also considered the availability of open source implementations and their suitability for the multimodal bias detection task. The use of an odd number of models in the annotation process ensured a clear majority vote to resolve any discrepancies.
The paper emphasizes the importance of data quality. Can you elaborate on the data collection process and the steps taken to ensure the quality and representativeness of the dataset?
The data was collected from a wide range of reputable news sources encompassing diverse political viewpoints and geographical regions. Pre-processing steps included removing duplicates, filtering out non-text-rich content, and pairing each article with its primary image. The inclusion of articles from previous work was carefully considered, ensuring that the new annotation framework enhanced robustness and reliability. The final dataset comprises approximately 41,412 articles, each paired with an image and annotated for bias.
The paper discusses the evaluation metrics used to assess model performance. Why were precision, recall, F1 score, and accuracy chosen, and what are the relative strengths and weaknesses of these metrics in this context?
Precision, recall, F1 scored, and accuracy are standard metrics for evaluating classification performance. Precision measures the proportion of correctly identified biased articles among all articles classified as biased. Recall measures the proportion of correctly identified biased articles among all actually biased articles. The F1 score balances precision and recall, while accuracy represents the overall correctness of the classification. In this context, the choice of these metrics allows for a comprehensive assessment of the model's performance across different aspects of bias detection. However, these metrics alone may not fully capture the nuances of bias, highlighting the need for qualitative analysis as well.
The paper mentions the use of a two-step voting mechanism to improve annotation reliability. Can you explain this mechanism in more detail and discuss its effectiveness in mitigating stochastic variations inherent in LLMs?
The two-step voting mechanism first aggregates annotations from 3 separate queries for each LLM, selecting the majority response. This step mitigates the stochasticity within a single model. Then, a second majority vote is performed across the 3 LLMs, further reducing the impact of individual model biases or inconsistencies. This approach significantly improves the reliability of the annotations, leading to a more robust and consistent dataset.
The paper describes the human validation process. How is this process designed to ensure the quality and fairness of the labeled data, and what level of inter-annotator agreement was achieved?
12 reviewers with expertise in computer science, media studies, political science, and linguistics reviewed a stratified sample of 10,000 annotations. They classified annotations as acceptable, needs improvement, or incorrect, providing written rationales. 2 subject matter experts guided the process, ensuring consistency and adherence to established bias identification protocols. The Inter-Annotator Agreement, IA, calculated using Cohen's kappa, reached 0.72, indicating substantial agreement between automated labels and expert judgments.
The paper provides a detailed description of the experimental setup, including the hardware and software used. Why was this level of detail included, and what is its importance for reproducibility?
Providing detailed information about the experimental setup, including hardware specifications, NVIDIA A100 GPUs, CLDA 12.1, software versions, Python 3.10, PyTorch 2.0, Hugging Face transformers, and hyperparameters is crucial for reproducibility. This allows other researchers to replicate the experiments and validate the findings, ensuring the reliability and trustworthiness of the research.
The paper mentions the use of various hyperparameters during model training and evaluation. Can you discuss the rationale behind the choices made for these hyperparameters and their impact on model performance?
The hyperparameter choices were guided by best practices in deep learning and aimed to optimize performance while managing computational resources. The use of mixed precision training, torch.bfloat16, balanced memory efficiency and numerical accuracy. Flash attention to accelerated attention computations, particularly for larger models. Quantization techniques were employed for LLMs and VLMs to reduce memory requirements and speed up inference. These choices were carefully considered to ensure both efficient training and accurate results.
The paper presents a comprehensive analysis of the results, comparing the performance of SLMs and LLMs across different configurations. What are the key takeaways from this comparative analysis?
The comparative analysis revealed that while SLMs offer computational efficiency, LLMs generally achieved higher accuracy, especially with instruction fine-tuning. The best-performing models varied depending on the task, text-only versus multimodal, and the training configuration, zero-shot, few-shot, fine-tuning. This highlights the importance of selecting the appropriate model and training strategy based on the specific needs and resource constraints of the application.
The discussion of ablation studies is particularly insightful. Can you elaborate on the findings regarding the impact of different fine-tuning techniques on model performance?
The ablation studies compared full fine-tuning with parameter-efficient fine-tuning methods like LORA and prefix tuning. Full fine-tuning achieved the best performance, but LORA provided a strong alternative, achieving near parity with full fine-tuning while significantly reducing computational costs. Prefix tuning showed a larger performance drop, suggesting that LORA is a more effective parameter-efficient method for this task. These findings are important for practical applications where computational resources are limited.
The paper concludes with a discussion of the limitations of the study and directions for future research. What are some of the most important limitations to address in future work?
The limitations include the potential bias in the dataset itself, the focus on readily detectable biases, and the computational cost of using large models. Future work should address these limitations by expanding the dataset to include a wider range of cultures, languages, and bias types, developing more sophisticated methods for detecting subtle biases, and exploring more efficient model architectures or training techniques. Investigating the generalizability of the findings across different languages and cultural contexts is also crucial.
This has been a very thorough discussion of the VilBias paper. Thank you for insightful contributions.